everywhere. And why is that? It's precisely because it has to be rigid, but at the same time, the arm itself, the movable parts, they cannot be as heavy as you want, because they have to move freely and follow the track, the groove, and all this movement has the force to do this movement is provided only by the deflection of the cantilever and the suspension. So these are very tiny forces. So if you want to move this part with tiny forces, it cannot be as heavy as you want. Which the ideal would be to build it like a brick, but it's not working in this case. If you look at how the lathes, the cutting lathes for cutting lacquers are built, they are massive. They are nowhere near this kind of dimensions and materials. They are really a big chunk of metal, but they are not being driven by the groove. They are creating the groove themselves, so they can be made, and they are controlled by computers. It's in this case when we have to read the signal, the groove, you cannot impose where the arm or the cartridge has to be. You have to allow the groove to dictate that. So it has to be at the same time very rigid and not too heavy. So, but if you can pass it around, and you will feel that it's quite substantial in size and mass. And even all the supporting structures, like the bearings, are really massive and rigid also to hold the rest of the arm tube and the head shell with as less movement as possible. The SAT pickup arm is designed as a pivoted arm, and I choose to do it this way and not go for a tangential arm, because I believe that the angular error, because of being a radial arm, is so small compared to the disadvantages that you get with a properly designed tangential arm, that it's not worth it. The tangential arm should require a high mass to be stiff, and it should be, this mass would be much higher in the horizontal plane, much higher than what you get with a pivoted arm of the same stiffness. So that would affect much more the quality of the sound than what the small angular error you get with a pivoted arm, even if it's only a 9-inch arm like this one. So it's a pivoted arm with a gimbal bearing. It has 2 axes with pivots on them, and they can be adjusted in preloading, so that you can get higher preload, which makes them more rigid also, but you get higher friction, and that works better with low compliance or stiff cartridges. And the opposite, if you decrease the preload, you get less friction, lower stiffness, and it works better than with high compliance or soft suspension cartridges. So that's something that can be tailored for every specific cartridge and get most of their performance. Another feature which is important to consider for the arm is that the arm tube and the head shell, which are the most important components in terms of performance of the arm, they are made out of carbon fiber laminates, and the reason for that is to achieve high stiffness with low weight. So the stiffness to weight ratio is much higher than with metals. And they are the tube and the head shell. They are custom designed from the ground up. There's no standard component there. Everything has been designed specifically for that function and this arm by myself, and it's made out of more than 20 plies of specific geometries and laid up in specific a specific sequence and direction, orientation, to achieve the required final properties. And the same goes for the head shell, which is made of the same material, and in that case it consists of more than 40 plies. So it's a lot of, and it's a hand work, let's say, or handmade process, yeah. And
how long does it take to make one?
It takes you mean the layup itself? It takes maybe 4 hours or just for the layup itself. But then it has to be cut and prepared and so on. And we use what it's called a ply book, for example. It's like a receipt, like a cooking receipt. It tells you which ply, which piece of material you have to take, and in what sequence and what orientation. And that's very important because it determines the properties of the component. The head shell is detachable, and it can be rotated to adjust azimuth. And
you're saying each layer is 4 hours. The whole arm?
No. The tube, just the hand layup of the tube.
I see.
But that's not the whole process. Yeah. It's just one part of it. And it's CNC cut. That means it's computerized controlled cutting, so that all the pieces are exactly as they are designed from the CAD software, and they are always cut in the same size and match exactly as they should every time, not by hand, not cut by hand. So, looking at the arm, there's nothing really which is groundbreaking in terms of features, which you cannot find in any other arm. It's I mean, I don't have any patent for anything. It's most of the features are existing already in some other designs, but I believe what I've done is to gather what's best of what has been done until now. And of course there are some unique things like the arm tube and the head shell. There's nothing similar, and that's a big part of why the arm performs the way it does. So.